Complex compounds are a special class of compounds in which the metal atoms or ions are bound to a number of anions or neutral molecules. In modern terminology, these compounds are called coordination compounds. Coordination compounds or complex compounds are a type of addition compounds. When two or more stable compounds are allowed to combine in stoichiometric ratios, crystalline compounds are formed. These are known as addition or molecular compounds. For example, when saturated solutions of potassium sulfate and aluminium sulfate are mixed and heated till the crystallization point is reached, we get the well-known compound potash alum. Similarly, if we add a solution of potassium cyanide to a white precipitate of nickel cyanide, the precipitate immediately dissolves, and a red-orange solution of a new compound is obtained. On the basis of their nature, addition or molecular compounds are divided into two categories. They are double salts and coordination or complex compounds. Double salts are molecular compounds that are stable in the solid state but break down into individual constituents when dissolved in water. Note that the individual properties of the constituents are not lost in these compounds. For example, an aqueous solution of potash alum will give the tests for K+, Al+3 and SO4-2 ions. Other common examples of this class include carnallite and Moore's salt. On the other hand, coordination compounds are molecular compounds that retain their identity even when dissolved in water. Note that the individual properties of the constituents are lost in these compounds. For example, when potassium ferrocyanide is dissolved in water, it does not give the usual tests for Fe+2 and Cn- ions, indicating that the ion FeCN6-4 does not dissociate into Fe+2 and Cn- ions. Other familiar examples for nickel, copper, and silver are shown here. Actually, these ions are present in the form of a new ion called a complex ion. Compounds that have complex ions are called complex compounds. as the central metal ion in the complex ion forms dative or coordinate covalent bonds with the species surrounding it. Complex ions are also known as coordinate ions, and hence the corresponding compounds as coordinate compounds. Transition metals show a greater tendency to form complex compounds. This is due to the relatively smaller size of the metal ions, high ionic charges, and the availability of vacant d orbitals for bond formation. Coordination compounds form the backbone of modern inorganic and bioinorganic chemistry and chemical industry. Naturally occurring complex compounds are vital to living organisms. For example, chlorophyll is a coordination complex of magnesium. Hemoglobin is a coordination complex of iron. While vitamin B12 is a coordination complex of cobalt. Complex compounds find extensive use in electroplating, metallurgical processes, textile dyeing, and medicinal chemistry. Apart from that, they also find applications as industrial catalysts and analytical reagents. A coordination complex is the product of a Lewis acid-base reaction, in which a central metal atom or ion forms coordinate covalent bonds with neutral molecules or anions called ligands. Similar to the terms central metal and ligand, there are some other terms like coordination number, coordination sphere, coordination polyhedron, oxidation number, homoleptic complex, and heteroleptic complex, which are used with reference to coordinate compounds. Hence, you must get familiarized with these terms to understand different aspects of coordination chemistry. So let's go through these terms in detail. The first term is central metal atom or ion. The atom or ion to which one or more neutral molecules or anions are attached in a definite geometrical arrangement around it is called the central atom or ion. For example, the central metal ion in NiNH3 6 plus 2 is Ni plus 2, in FeCN6 minus 3 is Fe plus 3, and in COCl6 minus 3, it is the CO plus 3 ion. As the central metal atom or ion acts as an electron pair acceptor, it is also referred to as a Lewis acid. Another important term is ligand. A ligand is any atom, ion, or molecule capable of donating a pair of electrons to the central atom. A ligand is also known as a coordination group. As ligands are electron pair donors, they act as Lewis bases. Ligands may be simple ions such as halide ions, small molecules such as water or ammonia, or large molecules such as ethane 1,2-diamine or ethylene diamine tetraacetate ion. The number of atoms in a ligand that bind to the central atom in a complex is referred to as denticity. When a ligand is bound to a metal ion through a single donor atom, as with a chloride ion, a water molecule or an ammonia molecule, the ligand is said to be unidentate. Ligands that contain two donor atoms are known as bidentate or didentate. Common examples of didentate ligands are ethane 1,2-diamine, dimethylglyoxime, and oxalate ion. As you can see, these ligands have two donor atoms that can simultaneously bind to the central metal atom. Ligands with several donor atoms are called polydentate or multidentate ligands. A classic example of polydentate ligand is the hexadentate ligand, ethylene diamine tetraacetate ion, EDTA. You can see from its structure that it binds to the central metal ion through 2 nitrogen and 4 oxygen atoms. Ligands like ethylene diamine and EDTA, which have lone pairs of electrons on more than one atom, are capable of binding to the central metal atom or ion through more than one coordinate covalent bond. Such ligands are called chelating ligands. Some ligands have two different types of potential donor atoms, but use only one of them to form a coordinate covalent bond with the metal ion. Such ligands are called ambidentate ligands. The NO2- ion is one such ambidentate ligand capable of coordinating to the metal atom or ion through the nitrogen or oxygen atom. Similarly, the SCN- ion can coordinate through the sulfur or nitrogen atom. Now, let's look at another important term, coordination number. The total number of ligand donor atoms to which the metal is directly bonded is known as the coordination number of that ion. For example, the coordination number of silver in the complex ion AgNH32+ is 2, while that of nickel in the NiNH3 4+2 ion is 4. Similarly, the coordination number of copper in CuEn2+2, a complex with a didentate ligand, is 4, while that of cobalt in COC2O4 3-3, another complex with a didentate ligand, is 6. Coordination entity or coordination sphere is a common term we use with reference to complexes. The central metal atom and the ligands attached to it are collectively termed as the coordination sphere or coordination entity. For example, in the complex K4FeCN6, Fe, along with the 6 cyanide ligands, is the coordination sphere. the coordination sphere is written inside square brackets, while the ionizable groups are written outside the bracket and are called counterions. For example, in the complex K2NiCl4, the coordination sphere is NiCl4 minus 2, and the counterion is potassium. Coordination polyhedron is another term we use in coordination chemistry. In a coordination sphere or entity, the ligands are attached to the central metal ion in such a way that it gives a definite geometry to the complex. Thus, in a coordination entity, the solid figure defined by the position of the ligand atoms directly attached to the central atom or ion is known as the coordination polyhedron. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. For example, CONH3 6 plus 3 is octahedral. NiCO4 is tetrahedral, while PtCl4 minus 2 is square planar. One of the most important terms we often use is oxidation number of the central atom. The oxidation number of the central metal atom in a complex is defined as the electric charge it would carry if all the ligands were removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by a Roman numeral in parentheses after the name of the central metal atom. For example, the oxidation number of iron in FeCN6-3 is plus 3, and it is written as Fe3. Let us learn the method to determine the oxidation number of the central metal atom in a complex. Let's take K4FeCN6 as an example. As the complex has 4 monovalent cations outside the coordination sphere, the complex ion carries a charge of minus 4. That is, FeCN6 minus 4. Let's assume the oxidation number of the central metal atom as X. The cyanide ion is a monodentate negative ion. Knowing that the complex carries a charge of minus 4 and has 6 monodentate negative ions, the oxidation number of iron can be determined as X plus 6 multiplied by minus 1, which is equal to minus 4. On simplification, we get X is equal to plus 2. Thus, the oxidation state of iron in the given complex is plus 2. Here is a simple problem for you. Calculate the oxidation number of the metal atoms in the complexes given here. In the first case, there are 3 cations outside the coordination sphere. Hence, the charge on the complex ion is minus 3. The oxalate ion is a bidentate ligand. Each oxalate ion carries a charge of minus 2. The oxidation number of iron, which is assumed as X, is calculated as X plus 3 multiplied by minus 2, which is equal to minus 3. On simplification, we get X is equal to plus 3. Hence, the oxidation number of iron is plus 3. Similarly, the oxidation number of copper and silver in the other two complexes are calculated as +2 and +1 as shown. Finally, let's look at the terms homoleptic complex and heteroleptic complex. A complex in which a metal is bound to only one type of ligand atoms is known as a homoleptic complex. For example, CONH3 6 plus 3 and FeCN 6 minus 3. On the other hand, a complex in which a metal is bound to more than one kind of ligand atoms is called a heteroleptic complex. For example, CONH3 4ClBr plus 1 and CrNH3 4Cl2 plus 1. Have you ever wondered why a stable salt, such as cobalt trichloride, combines with a group of stable, independently existing molecules, such as ammonia, to form new compounds like COCl3, 6NH3, COCl3, 5NH3, and COCl3, 4NH3 with entirely new properties? Alfred Werner, a Swiss chemist, after preparing thousands of new compounds and studying their properties, put forward a theory to explain the formation of complex compounds. It was the first successful explanation for the phenomenon. The theory became famous as the coordination theory of complex compounds, which is also known as Werner's theory. His explanation of complex formation is based on some postulates. The first postulate is that the central metal atom or ion in a coordination compound exhibits two types of valencies, primary and secondary. While writing the structure of the metal complexes, the ligands that are linked by primary valency are shown by dotted lines, while those linked by a secondary valency are shown by thick lines. If a ligand satisfies both the valencies, then it is shown by a thick as well as by a dotted line, and it is said to exhibit dual character. The second postulate is that primary valencies are ionizable and correspond to the number of charges on the complex ion. Primary valencies apply equally well to simple salts and to complexes, and are satisfied by negative ions. For example, the primary valency of 2 in COCl2 is satisfied by 2 chloride ions. Similarly, the primary valency of 3 in the complex CONH3 6Cl3 is satisfied by 3 chloride ions. In modern terminology, the primary valency corresponds to the oxidation number. The third postulate is that secondary valencies correspond to the valencies that a metal atom or ion exercises towards neutral molecules or negative ions in the formation of its complex ions. Every metal has a fixed number of secondary valencies or coordination number. For example, cobalt 3+, platinum 4+, and iron 3 plus ions are recognized to have a coordination number of 6. Similarly, nickel 2 plus, copper 2 plus, and platinum 2 plus ions have a coordination number of 4. Secondary valencies are non-ionizable. They are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number of the metal. For example, in the complex COCl3 6NH3, the 3 chlorides are held by primary valencies and the 6 ammonia ligands are held by secondary valencies. The fourth postulate is that secondary valencies are directional, and so a complex has a particular shape. The number and arrangement of ligands in space determines the stereochemistry of a complex. The most common coordination number in transition metal complexes is 6, and the shape is usually octahedral. The coordination number 4 is also common, and this gives rise to either tetrahedral or square planar complexes. This postulate predicted the existence of isomerism in coordination compounds. To distinguish between the two types of valencies, Werner introduced the concept of using square brackets to enclose the atoms that make up a coordination complex and which are, therefore, not ionized. The postulates of Werner's coordination theory were actually based on experimental evidence rather than theoretical. Werner treated cold solutions of a series of compounds of cobalt 3 chloride with ammonia with an excess of silver nitrate and weighed the silver chloride precipitated. The stoichiometries of the complex silver chloride formed were as shown here. Werner deduced that in COCl3 6NH3, the primary valency or oxidation state of +3 is satisfied by 3 chloride ions. The coordination number of the cobalt 3 plus ion is 6. As there are 6 ammonia molecules in the compound, they alone satisfy the 6 secondary valencies of cobalt. As you can see, the primary valencies are represented by dotted lines and the secondary valencies by thick lines. In modern terms, the complex is written as CONH3 6Cl3. The 3 chloride ions are ionic and hence are precipitated as silver chloride by silver nitrate. Thus, the complex will ionize in solution and give 4 ions. That is, 1 CONH3 3 plus ion and 3 chloride ions. Werner deduced that the loss of one ammonia molecule from COCl3 6NH3 should give COCl3 5NH3. This complex has only 5 ammonia molecules. Therefore, to satisfy the coordination number of 6 of cobalt, one chloride ion assumes dual behavior. That is, it satisfies the primary as well as the secondary valency of cobalt. In modern terms, the complex can be written as CONH3 5Cl Cl2. Thus, only 2 of the 3 chloride ions are ionic, and thus only 2 are precipitated as silver chloride with silver nitrate. On ionization, this complex will give 3 ions: 1 CONH3 5Cl 2 plus ion and 2 chloride ions. As can be seen from its structure, one chloride ion, which is playing a dual role, is shown by a thick as well as a dotted line. Similarly, in COCl3 4NH3, to satisfy the secondary valency of 6, 2 chloride ions assume dual behavior. In modern terms, the complex can be written as CONH3 4Cl2 Cl. Thus, only one chloride ion can be precipitated as silver chloride. This complex, on ionization, gives 2 ions: one of CONH3 4Cl2 plus and the other of chloride ion. The structure of the complex is shown here. Although Werner's theory successfully explains the bonding features in coordination compounds, it suffers from some drawbacks. It doesn't explain why only certain elements form coordination compounds. It does not explain why the bonds in coordination compounds have directional properties. It does not explain the color and the magnetic and optical properties of complexes. An important aspect of coordination chemistry is the nomenclature of coordination compounds. The names and formulae of coordination compounds are written by employing the rules published by the International Union of Pure and Applied Chemistry, or IUPAC in short. Let's look at the rules framed by IUPAC for writing the formula of a complex. The first rule is the formula of the cation, whether it is simple or complex, is written first, followed by that of the anion. For example, in the complex shown here, the cation sodium is written first, followed by the anionic coordination entity. Similarly, in the complex containing a complex cation and a complex anion shown here, the complex cation AgNH32 is written first, followed by the complex anion AgCN2. The second rule is that within the coordination sphere, the symbol of the central atom is written first, followed by the symbols or formulas for the ligands in alphabetical order, irrespective of the charge on them. For example, in the complex shown here, the metal atom cobalt is written first, followed by the ligands ammonia and chloride. Polydentate ligands are also listed alphabetically. While listing in alphabetical order, the first letter of the abbreviation of the ligands is used to determine their position. For example, if a complex contains chloride and ethane 1,2-diamine, which is abbreviated as En, then in alphabetical order, chloride is written first, followed by ethane 1,2-diamine. Another rule is that the formula for the entire coordination sphere is enclosed in square brackets. For example, in the complex shown here, the coordination sphere containing the metal atom copper with 4 bromine atoms are enclosed in square brackets. The cation potassium is written outside the coordination sphere. The formulae for polyatomic ligands and the abbreviations used for the ligands are enclosed in brackets. For example, En, EDTA, PY, etc. are enclosed in brackets. For example, in the complex of cobalt shown here, the coordination entity contains the polyatomic ammonia ligand and the abbreviated ethane 1,2-diamine ligand enclosed in brackets. One more rule is within a coordination sphere, the metal atom as well as the ligands are listed without any space between them. For example, in the complex of cobalt shown here, the ligands ammonia, water and chloride are listed without any space between them. Yet another rule is that when the formula for a cationic or anionic coordination sphere is to be written without that of the counter-ion, then the charge with the number before the sign is written as a right superscript outside square brackets. For example, the complex ions of cobalt and chromium with the charge on the respective ions are shown here. Now let's see the IUPAC recommendations for writing the names of complexes. The first rule is for coordination compounds that are ionic, that is, the coordination sphere serves either as the cation or the anion of the ionic substance, the cation is named first and separated by a space from the anion. For example, in the complex K4FeCN6, where the coordination sphere is an anion, the cation potassium is named first and separated by a space from the name of the anion. On the other hand, in a complex such as CONH3 6Cl3, where the coordination sphere is a cation, the cationic coordination sphere is named first, followed by the name of the counter-anion, chloride. The second rule is, while naming the coordination sphere, ligands are named first, followed by the name of the central metal atom or ion with its oxidation state in Roman numerals in parentheses. Remember that irrespective of the charge on the ligands, they are named in alphabetical order. For example, in the complex PT-NH3 2Cl4, the ammonia ligands are named before the chloride ligands according to the alphabetical order, followed by the name of the metal ion with its oxidation number enclosed in brackets. IUPAC has also proposed certain rules for naming ligands. Anionic ligands are given names that end in the letter O. When the name of the free uncoordinated anion ends in ate, the name of the ligand is changed to end in ato, ATO. For example, the anion acetate is named acetato, sulfate as sulfato, thiocyanate as thiocyanato, and carbonate as carbonato. When the name of the free uncoordinated anion ends in ide, IDE, the ligand name is changed to end in ido, IDO. For example, the anion fluoride is named fluorido, chloride as chlorido, bromide as bromido, and iodide as iodido. Similarly, nitride is named nitrido, amide as amido, and azide as azido. Neutral ligands are given the same name as the uncoordinated molecule. For example, pyridine, dinitrogen, dioxygen, and triphenylphosphine. However, some neutral ligands are given special names. They are aqua for water, amine for ammonia, nitrosyl for nitric oxide, and carbonyl for carbon monoxide. Positive ligands, such as nitronium, hydrazinium, and nitrosodium, are named as such without any change. Another rule says, if several ligands of the same type are attached to the central metal atom, then their number is indicated by the prefixes di, tri, tetra, penta, etc. For example, in the complex CONH3 3H2O Cl2, the 3-amine and 2-chlorido ligands are indicated by the prefixes tri and di, respectively. However, if the name of the ligand in question already includes a numerical prefix, then the prefixes like bis, tris, tetrakis, and pentakis are used. For example, the complex RuCl3 PPH33 is named as tris-triphenylphosphine trichlorido ruthenium 3. Here's another rule. When the coordination entity is either neutral or cationic, the usual name of the metal is used. For example, the neutral complex shown here is named triamine trichlorido cobalt 3. Similarly, the cationic complex CrH2O4Cl2Cl is named tetra-aqua-dichloridochromum 3-chloride. Note that, in either case, the usual name of the metal is retained. However, when the coordination entity is an anion, the name of the metal ends with the suffix -ate. For example, the anionic complex NaPtNH3 3Cl3 is named as sodium triamine trichloridoplatinate 2. For some metals such as iron, copper, silver and gold, their Latin names ferrate, cuprate, argentate and aurate are used. For example, the complex K2CuCl4 is named potassium tetrachloridocuprate 2. Similarly, the complex NaAgCN2 is named sodium dicyanoargentate 1. Now is the time for practice. Apply IUPAC rules for writing the formulae in the first question and for writing the IUPAC names for the given complexes in the second question. Question 1. Write the formulae for these coordination compounds. Tetraamine aqua chloridocobalt 3-chloride. Dichlorido bis ethane 1,2-diamine cobalt 3. Tetracarbonyl nickel 0. Question 2. Write the IUPAC names of these coordination compounds. Let's write the formula for the first complex. The coordination sphere is the cationic part in this complex. For writing the coordination entity, the symbol of the metal is written first, followed by the symbol or formula for the ligands. Hence, the coordination sphere is written as CO followed by NH3 and H2O ligands in brackets, followed by Cl. The next task is to balance the charge on the cation with the charge on the anion. Since amine and aqua ligands are neutral, and there is only one chloride ligand inside the coordination sphere, the charge on the complex ion is +2. Hence, two anions can neutralize the charge on the cation. Thus, the formula for the given compound is CONH3 4H2O ClCl2. Similarly, the formulae for the other two complexes are written as shown here. Coming to the second question. The first complex is a cationic complex and has two chloride ligands and two ethane 1,2-diamine ligands. The oxidation number of cobalt, as calculated here, is +3. Following the alphabetical order in naming the complex, chlorido-ligands are named first, followed by ethane 1,2-diamine. The number of chloride and ethane 1,2-diamine ligands is indicated by the prefixes di and bis respectively. Thus, the IUPAC name of the given complex is written as dichlorido bis ethane 1,2-diamine cobalt 3. Similarly, The IUPAC names of the other complexes are written as shown here. To explain the metal to ligand bonding in complex compounds. Different theories, such as the valence bond theory, crystal field theory, ligand field theory, and molecular orbital theory were proposed. Among these theories, the valence bond theory is the simplest, which satisfactorily explains the structure and magnetic properties of a large number of coordination compounds. The valence bond theory was proposed and developed by Linus Pauling. Here are some salient features of the theory. The central metal atom, or ion, has the required number of vacant orbitals for accommodating the electrons, donated by the ligands. The number of vacant orbitals is equal to the coordination number of the metal ion for a particular complex. The vacant orbitals of the metal atom or ion undergo suitable hybridization to yield a set of equivalent hybrid orbitals of definite geometry. The geometry of the complex can be predicted based on the coordination number and the hybridization of the metal atom or ion. As you can see from the table, when the coordination number is 4, the metal atom or ion may undergo either sp3 or dsp2 hybridization, and the complex may assume either tetrahedral or square planar geometry. When the coordination number is 5, the metal ion undergoes sp3 dehybridization, and the complex has trigonal bipyramidal geometry. When the coordination number is 6, the metal ion may undergo either sp3d2 or d2sp3 hybridization. In either case, the complex has octahedral geometry. A ligand orbital containing a lone pair of electrons forms a coordinate covalent bond by overlapping with the hybrid orbitals of the metal ion. The magnetic moment of the complex can be used to determine its geometry. Note that the magnetic moment of coordination compounds can be measured by magnetic susceptibility experiments using a Gauss balance. The results of the experiments can be used to work out the shape of the complex. In the formation of a complex, if the metal utilizes its inner d orbitals, then such a complex is called an inner orbital complex or low spin or spin paired complex. On the other hand, if the metal utilizes its outer orbitals for complex formation, then such a complex is called an outer orbital complex or high spin or spin-free complex. Now let's apply these postulates to a dimagnetic complex, hexaamine cobalt 3 chloride. The cobalt atom in its ground state has the electronic configuration of argon 3d7 4s2. In the given complex, the cobalt is in +3 oxidation state. Thus, the cobalt +3 ion will have the configuration of 3d6 4s0. A glance at the configuration indicates that the complex is paramagnetic due to the presence of 4 unpaired electrons. Magnetic studies, on the other hand, have revealed that the given complex is dimagnetic in nature. This is possible only when the 4 unpaired electrons in the 3d orbital get paired up contrary to the Hund's rule. As a result of electron pairing, 2 vacant 3d orbitals are made available for hybridization. Thus, 2 3d, 1 4s and the 3 4p orbitals hybridize together to give a set of 6 equivalent d2sp3 hybrid orbitals. The 6 pairs of electrons donated by the 6 ammonia ligands occupy the 6 hybrid orbitals. You can see that there are no unpaired electrons left in the metal ion. Thus, the complex is dimagnetic and has octahedral geometry. As you can see, the metal ion has utilized its inner 3d orbitals for the formation of the complex. Hence, this complex can be called an inner orbital or low spin or spin paired complex. Similarly, in the case of complex ions such as hexaamine manganese 3 or hexacyanoferrate 2, pairing takes place contrary to Hund's rule, resulting in the formation of dimagnetic inner orbital complexes with d2sp3 hybridization. Now let us examine a paramagnetic complex, sodium hexafluorido cobaltate 3. In this complex also, cobalt is in +3 oxidation state. Magnetic studies indicate the paramagnetic nature of the complex. This is possible only when the outer 4s, 4p and 4d orbitals undergo hybridization. Thus, the cobalt ion undergoes sp3d2 hybridization and has octahedral geometry. As the outer d orbitals are utilized for hybridization, the complex is also called an outer orbital complex or high spin or spin-free complex. Similarly, in the complex ions, hexachlorido manganate 3 and hexafluorido ferrate 3, the outer 4s, 4p and 4d orbitals get involved in the hybridization to form outer orbital paramagnetic complexes with 4 and 5 unpaired electrons respectively. However, note that in the case of octahedral complexes formed by metal ions, such as titanium 3+, vanadium 3+, and chromium 3+, which have 1, 2, and 3 unpaired electrons, the magnetic behavior of these free metal ions and their coordination entities is similar. As you can see, in these ions, there are 2 vacant d orbitals available for octahedral hybridization with 4s and 4p orbitals. Thus, these octahedral complexes are always paramagnetic in nature. Now let's study complexes with the coordination number 4. You know that when the coordination number is 4, the complex may either have tetrahedral geometry or square planar geometry. We will first examine a paramagnetic tetrahedral complex, potassium tetrachlorido nickelate 2. In this complex, nickel is in +2 oxidation state. and thus has the configuration of argon 3d8. The complex can be paramagnetic only if nickel undergoes sp3 hybridization and not dsp2 hybridization. Thus, the 4s and 4p orbitals hybridize together to give a set of 4 sp3 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in the hybrid orbitals. Hence, the given complex assumes tetrahedral geometry. Tetracarbonyl nickel 0 is an interesting example of dimagnetic tetrahedral complex. In this complex, the metal atom nickel is in zero oxidation state. Experimental studies suggest this complex to be dimagnetic in nature. This is possible only when the paired electrons in the outer 4s orbital pair with the electrons in the 3d orbital. Thus, the metal atom undergoes sp3 hybridization to result in 4 sp3 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in these orbitals. Hence, the complex is a dimagnetic tetrahedral complex. Now, let us examine a dimagnetic square planar complex, tetracyanonickelate 2. In this complex, nickel is in +2 oxidation state and has the electronic configuration of argon 3d8. Magnetic studies suggest this to be a dimagnetic complex. This is possible only when the 2 unpaired electrons in the 3d orbital get paired up. Thus, the vacant 3d, 4s, and 2 of the 3 4p orbitals hybridize to form a set of 4 dsp2 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in these orbitals. The complex so formed has square planar geometry. Here is a question for you. What is the geometry of the complex if the spin-only magnetic moment of potassium tetrabromido manganate 2 is 5.9 Bohr magnetons? The coordination number of the Mn+2 ion in the given complex is 4. Hence, it may either undergo sp3 or dsp2 hybridization, and may have either tetrahedral or square planar geometry. However, the magnetic moment value of 5.9 Bohr magnetons clearly indicates the presence of 5 unpaired electrons in the complex. This is possible only when the metal ion undergoes sp3 hybridization. Thus, the given complex has tetrahedral geometry. Let us now look at the shortcomings of the valence bond theory. Although the valence bond theory successfully explains the formation, geometry and magnetic behavior of coordination compounds, it suffers from certain drawbacks. They are: coordination compounds are generally colored, but the valence bond theory does not explain the color exhibited by these compounds. This theory does not provide a quantitative interpretation of the stability of the complexes. It does not give the quantitative interpretation of magnetic data. It fails to predict the exact geometry of complexes with coordination number 4. For example, according to the valence bond theory, CuNH342 plus has tetrahedral geometry. But X-ray analysis has proved that this complex has square planar geometry. The crystal field theory was proposed by Hans Bethe and Van Vleck. This theory gives a much more satisfactory explanation for the bonding and the properties of complexes than the valence bond theory. The crystal field theory is based on certain assumptions. The interaction between the metal ion and the ligand is purely electrostatic. That is, the metal-ligand bonds are 100% ionic in nature. Negative ligands are treated as point charges, and neutral ligands are treated as dipoles. Thus, the bonding in the complex may be an ion-ion interaction or an ion-dipole interaction. The 5d orbitals in an isolated gaseous metal atom or ion are degenerate. That is, they all have the same energy. However, when the ligands approach the metal ion to form a complex, the electrons in the d orbitals of the metal will be repelled by the negative charge or lone pair electrons of the ligands due to the repulsion between the like charges. As a result, the energy of the d orbitals increases and the degeneracy of the d orbitals is lifted. It results in the splitting of the d orbitals. The pattern of splitting of the d orbitals depends on the number of ligands and their arrangement around the central metal atom or ion. Let's look at the application of the crystal field theory to octahedral complexes. In octahedral complexes, the metal ion is at the center of the octahedron, and the 6 ligands lie at the 6 corners of the octahedron along the 3 axes X, Y, and Z as shown here. The approach of the ligands towards the central metal ion is considered a 2-step process. In the first step, it is assumed that the ligands approach the metal ion spherically, that is, at the same distance from each d orbital. At this stage, the energy of all the d orbitals is raised by the same amount. That is, the 5 d orbitals still remain degenerate. The average value of the energy of the d orbitals at this stage is taken as 0, and this is called the Barry center. However, out of the 5 d orbitals, 2, that is, the dx square minus y square and dz square orbitals, which are collectively known as the EG set of orbitals, are oriented along the axes towards the direction of the ligands. Thus, the EG set of orbitals will experience more repulsion than the remaining 3 d orbitals, that is, the dxy, dxz, and dyz orbitals. which lie in between the axes. These 3 d orbitals are collectively known as the T2g set of orbitals. Consequently, the energy of the Eg set of orbitals increases, while that of the T2g set decreases relative to the average energy in the spherical crystal field. Thus, under the influence of the ligands, the degeneracy of the 5 d orbitals of the metal ion is lost, and they are split into 2 groups of different energies. This effect is known as crystal field splitting. The extent of the splitting in energies is represented by the symbol delta O. The subscript O indicates octahedral geometry. Due to this splitting, the energy of the 2 Eg orbitals will increase by 3/5 of delta O, while that of the 3 T2g orbitals will decrease by 2/5 of delta O. The magnitude of crystal field splitting depends upon the field strength of the ligand and the charge on the metal ion. Ligands that cause only a small degree of crystal field splitting are termed weak field ligands, while ligands that cause a large splitting are called strong field ligands. In general, the common ligands can be arranged in ascending order of field strength as shown here. The order remains practically constant for different metals, and this series is called the spectrochemical series. It is an experimentally determined series based on the absorption of light by complexes with different ligands. Now, let's assign electrons in the d orbitals of the metal ion with d4 configuration in the octahedral coordination entities. Obviously, the first, second, and third electrons occupy the low-energy T2g orbitals in accordance with Hund's rule. However, for the fourth electron, there are 2 possibilities. The first possibility is that it may enter a T2g orbital and pair up with an existing electron there. The other possibility is that it may enter the higher Eg orbitals. The exact path followed by the electron depends on the relative magnitude of the crystal field splitting, delta O, and the energy required for the electron pairing in a single orbital, that is, pairing energy B. If the crystal field splitting energy is less than the pairing energy, then the fourth electron enters one of the higher energy Eg orbitals, giving the configuration T2G3 Eg1. Ligands for which the crystal field splitting energy is less than the pairing energy are known as weak field ligands. The complexes formed with these ligands would be high-spin complexes. If the crystal field splitting energy is higher than the pairing energy, then the fourth electron enters a T2g orbital and pairs up with one of the electrons, giving the configuration T2G4 Eg0. Ligands for which the crystal field splitting energy is higher than the pairing energy are known as strong field ligands. The complexes formed with these ligands would be the low-spin complexes. Now, let's look at the crystal field splitting in tetrahedral complexes. The approach of the ligands in a tetrahedral field is as shown in the figure. You can observe from the figure that the ligands interact more with the T2G orbitals than the EG orbitals lying between the axes. This is because the T2G orbitals are oriented along the direction of the approach of the ligands. Thus, in tetrahedral splitting, the T2G orbitals are of higher energy, and the two EG orbitals are of lower energy. You can say that the d orbital splitting in tetrahedral geometry is exactly the reverse of octahedral splitting. The crystal field splitting in tetrahedral complexes, which is denoted by delta T, is smaller than that of octahedral complexes. The difference in energy can be represented by delta T is equal to 4 by 9 times of octahedral splitting. This splitting energy is not large enough to force the electrons to get paired up. Thus, low-spin configurations are rarely observed. Transition metal atoms, or ions, with one or more unpaired electrons and their complexes exhibit color both in their solid and solution states. Let us see how a substance gets its color. When white light passes through a substance, it absorbs some of the wavelengths. The light transmitted by the substances is deprived of the wavelengths that have been absorbed. If absorption occurs in the visible region of the spectrum, then the transmitted light has a color complementary to the color of the light absorbed. Complementary color is the color generated from the wavelength left after the absorption. For example, for hexa-acure titanium 3+, the maximum absorption occurs at 498 nanometer, which corresponds to the blue-green portion of light. The transmitted light is devoid of the blue-green portion, and hence the complex appears purple. The relationship between the absorbed and transmitted wavelengths can be readily understood from the table here. The origin of the color of coordination compounds can be readily explained in terms of the crystal field theory. As you have studied in the previous module, when a ligand approaches the metal ion containing unpaired electrons, the 5 degenerate d orbitals separate into two distinct energy levels, namely T2G and EG. When light of sufficient energy is incident on the metal ion, the electron in the low-energy T2G orbital absorbs energy and gets promoted to the higher EG set of orbitals. White light minus the absorbed color becomes the color of the complex. Thus, the color of coordination compounds arises from the electron transition between the split d orbital energy levels. Let us take the example of hexa aqua titanium 3 to understand this. Hexa aqua titanium 3 is an octahedral complex in which titanium is in +3 oxidation state and has a single electron in the d orbital. The single electron is present in the lower T2G level in the ground state of the complex. When light passes through a solution of this complex, the electron in the lower T2G level is promoted to a higher Eg level by absorbing light with energy equal to the energy difference between the T2G and Eg levels. In this case, it absorbs energy corresponding to the blue-green region. As white light minus blue-green light gives purple color, the complex appears purple. The color of gemstones like ruby and emerald is also due to the d-to-d transition of electrons within the d orbitals of the transition metal ion. Ruby is a pink to blood red colored gemstone. It is aluminium oxide in which a small fraction of Al3+ ions are replaced by chromium 3+ ions. The red color of a ruby is mainly due to the presence of chromium 3 ions. We may view these chromium 3 ions as octahedral chromium 3 complexes incorporated into the alumina lattice. This crystallographic arrangement affects each chromium 3+ ion, resulting in the d-to-d transition of electrons after the absorption of the yellow-green portion of light. As white light minus yellow-green gives red color, a ruby looks red. Emerald is a green variety of the mineral beryl. The green color of emerald is due to the presence of chromium 3+ ions. The chromium 3+ ions occupy the octahedral sites in beryl. Due to this arrangement, it absorbs the yellow-red portion of light and, in turn, transmits the complementary color green. Hence, an emerald appears green. It is important to note that in the absence of a ligand, crystal field splitting does not occur. As a result, the substance remains colorless. For example, when hexa aqua titanium 3+ is dehydrated by heating it, it becomes colorless. Similarly, hydrated copper sulfate is blue, while anhydrous copper sulfate is colorless. The influence of the ligand on the color of a complex may be demonstrated by considering the hexa aqua nickel 2 complex. When nickel 2 chloride is dissolved in water, it gives the green hexa aqua nickel 2 complex. To this complex, if the didentate ligand ethane 1,2-diamine is added progressively in different molar ratios, different complexes with varying colors are formed. When the addition of ethane 1,2-diamine to the complex is in the molar ratio of 1:1. A pale blue-colored complex of tetra-aqua ethane 1,2-diamine nickel 2 is formed. When the addition is in the ratio of 2:1, a blue or purple-colored di-aqua bis ethane 1,2-diamine nickel 2 is formed. Addition in the ratio of 3:1 results in a violet-colored tris-ethane 1,2-diamine nickel 2 complex. Now let us see the drawbacks of the crystal field theory. Although it successfully explains the formation, structure, color, and magnetic properties of coordination compounds satisfactorily to a large extent, it suffers from some drawbacks. If the assumption that anionic ligands are point charges is correct, then anionic ligands should act as strong ligands, and hence should exert the greater splitting effect. However, anionic ligands are actually found at the low end of the spectrochemical series. The other drawback is that it does not take into account the covalent character of bonding between the ligand and the central atom. Two or more compounds with the same chemical formula but different structural arrangements are called isomers. The phenomenon is known as isomerism. Isomers differ in one or more physical or chemical properties because of the difference in the arrangement of the atoms. Isomerism in coordination compounds may be broadly divided into two types: structural isomerism and stereoisomerism. Structural isomerism arises due to the presence of different kinds of bonds between the metal and the ligands. This can be further subdivided into several types, like ionization isomerism, solvate isomerism, ligand isomerism, linkage isomerism, polymerization isomerism, coordination isomerism, and coordination position isomerism. Of these, we will discuss only ionization isomerism, solvate isomerism, linkage isomerism, and coordination isomerism in this module. Let us first discuss ionization isomerism. Compounds that have the same stoichiometric composition but yield different ions in a solution are called ionization isomers. This type of isomerism is due to the exchange of groups between the complex ion and the ions outside it. The composition can be determined by a precipitation reaction. Pentaamine sulfato-cobalt 3 bromide and pentaamine bromido-cobalt 3 sulfate are two ionization isomers. The first isomer gives a white precipitate of barium sulfate with barium chloride solution, thus confirming the presence of free sulfate ions. By contrast, the other isomer does not give a positive sulfate test. It does give a pale yellow precipitate of silver bromide with silver nitrate, confirming the presence of free bromide ions. Other examples of ionization isomers are tetraamine dichloridoplatinum 4 bromide and tetraamine dibromidoplatinum 4 chloride. Let us now look at solvate isomerism, which is similar to ionization isomerism. This form of isomerism is known as hydrate isomerism if water is involved as a solvent. Compounds that have the same composition but differ by whether or not solvent molecules are present as ligands in the coordination sphere or are merely present as free solvent molecules outside the coordination sphere are known as solvate isomers. 3 isomers of chromium chloride, hexahydrate, CrCl3, 6H2O, are known. From conductivity measurements and quantitative precipitation of the ionized chlorine, they have been identified as the violet-colored hexaaquochromium 3 chloride, the green-colored pentaaquochloridochromium 3 chloride hydrate, and the dark green-colored tetraaquodichloridochromium 3 chloride dihydrate. These isomers have different chemical properties. On reacting with silver nitrate to test for Cl ions, we would find 3, 2, and 1 chloride ions in the solution respectively. The other type of structural isomerism is linkage isomerism. Linkage isomerism arises when a ligand can bind to a metal ion through any one of 2 or more different donor atoms. Thus, this type of isomerism is seen in the coordination compounds that have ambidentate ligands. For example, in the ambidentate nitrite ion, either nitrogen or oxygen atoms could act as the electron pair donors. Thus, there is a possibility of isomerism. 2 different complexes, each containing nitrite ions, have been prepared. For example, red pentaamine nitritocobalt 3 chloride, in which the nitrite ligand is bound through oxygen, and yellow pentaamine nitrocobalt 3 chloride, in which the nitrite ligand is bound through nitrogen to the metal ion. Similarly, the thiocyanate ligand, SCN, may bind to the metal through sulfur to give complexes of the type MsCN, or through nitrogen to give MnCS type of complexes. Coordination isomerism is another type of structural isomerism. This type of isomerism arises when both the positive and negative ions are complex ions. It may be caused by an interchange of ligands between the anion and the cation. For example, in the complex hexaamine cobalt 3 and hexacyanochromate 3, the ammonia ligands are bound to the cobalt 3 plus ion, while the cyanide ligands are bound to the chromium 3 plus ions. In its coordination isomer, hexaamine chromium 3-hexacyanocobaltate 3. The ammonia ligands are bound to the chromium 3, while the cyanide ligands are bound to the cobalt 3+ ions. Let's now look at stereoisomerism. Compounds with the same chemical formula and chemical bonds, but different arrangement of atoms or groups in space, are called stereoisomers. Stereoisomerism can be subdivided into geometrical isomerism and optical isomerism. Geometrical isomerism is also known as cis-trans isomerism. It is seen in the heteroleptic complexes with coordination numbers 4 and 6. The isomer in which the two identical groups are adjacent to each other is known as a cis isomer, while the isomer in which the two identical groups are diagonally opposite to each other is known as a trans isomer. It is important to note that only square planar complexes show the phenomenon of geometrical isomerism, and not tetrahedral complexes. This is because the relative positions of the unidentate ligands attached to the central metal atom in the tetrahedral geometry are the same with respect to each other. In square planar complexes, compounds with the general formula Ma4 and Ma3b do not show geometrical isomerism. Here, M is a metal ion, while A and B are monodentate ligands. The square planar complexes shown here usually show cis-trans isomerism. The first complex is of the type Ma2b2. The best example of this type is diamine dichloridoplatinum 2. Both cis and trans isomers of this complex are shown here. The second complex is of the type Ma2bc. Diamine bromidochloridoplatinum 2 is an example of this type of complex. Another type of square planar complex is the MaBCD type. Platinum 2 forms a number of complexes of this type. Such complexes exist in 3 isomeric forms. For example, amine bromidochloridomyridine platinum 2. The 3 isomers of this complex can be seen here. Now, let's look at the geometrical isomerism in octahedral complexes. Ma6 or Ma5b types of octahedral complexes do not show geometrical isomerism. Complexes of the type Ma4b2 and Ma3b3 and complexes that have unidentate and symmetrical bidentate chelating ligands of the type MAA2b2 exhibit geometrical isomerism. Dichloridotetraamine cobalt 3 is an important example of a complex of the Ma4b2 type. The cis and trans isomers of this complex are shown here. An important Ma3b3 type of complex is trichlorido-tripyridine rhodium 3. In one of the isomers shown, you can see the 3 donor atoms of the same type of ligands occupying adjacent positions at the corners of an octahedral face. Such an isomer is known as a facial isomer. In the other isomer, called a meridional isomer, the position of the ligands are around the meridian of the octahedron. Now, let's look at MAA2B2 type of complexes containing monodentate and symmetrical bidentate chelating ligands. Here, AA is a symmetrical bidentate chelating ligand in which A and A indicate two similar coordinating atoms, while B is a monodentate ligand. The cis and trans isomers of dichlorido-bis-ethylene diamine cobalt-3 are shown here. Let's examine optical isomerism, which is the other type of stereoisomerism. When the solutions of certain coordination compounds are placed in the path of plane polarized light, they rotate its plane through a certain angle that may be either to the left or to the right. This property of a complex of rotating the plane of a polarized light is called its optical activity. A complex that possesses this property is said to be optically active. Complexes that rotate the plane of polarized light towards right are said to be dextro-rotatory or D-form, while complexes that rotated towards the left are called levorotatory or L-form. The D and L forms are mirror images and cannot be superimposed on each other. Such molecules or ions that cannot be superimposed are called chiral. Since these forms are related to each other as mirror images, they are commonly called enantiomers. Although optical isomerism is possible in a variety of octahedral complexes with unidentate ligands of the types Ma2b2c2, Ma2b2cd, Ma2bcde, and MABCDEF. We will restrict our discussion to complexes containing only bidentate ligands of the type MAA3 and complexes containing monodentate and symmetrical bidentate chelating ligands of the type MAA2B2. Tris-ethylene diamine cobalt-3 is the best example of an optically active coordination compound of the type MAA3, which has only bidentate ligands. The dextro and levo isomers of this complex are shown here. Dichlorido-bis-ethylene diamine platinum-4 is an example of an optically active coordination compound of the type MAA2B2 containing both monodentate and symmetrical bidentate ligands. Note that only the cis isomer of this complex shows optical activity. Its trans isomer shown here is optically inactive because its mirror image can be superimposed on itself. Carbonyls are coordination compounds of transition metals with carbon monoxide. Depending on the number of metal atoms, carbonyls are divided into two types: monomeric or mononuclear carbonyls and polynuclear carbonyls. Mononuclear carbonyls contain one metal atom per molecule. For example, tetracarbonyl nickel 0, pentacarbonyl iron 0, hexacarbonyl chromium 0 and hexacarbonyl tungsten 0. On the other hand, polynuclear carbonyls contain two or more than two metal atoms per molecule. For example, decacarbonyl dimanganese 0, octacarbonyl dicobalt 0, octacarbonyl dirhodium 0 and decacarbonyl dirhenium 0. It is important to note that in carbonyls, the electrons that form the chemical bond between the metal and the carbon of carbon monoxide are supplied solely by the molecules of CO. Hence, the metal atom is said to be in zero oxidation state. In a metal carbonyl, the metal-carbon bond has sigma as well as pi character. A sigma bond between a metal and a carbon is formed by the donation of a lone pair of electrons on the carbon of the CO molecule to a vacant orbital of the metal. A second bond is formed by back bonding. This bond is a metal-to-carbon pi bond formed by the sideways overlap of a full dxy orbital of the metal, with the empty antibonding pi star 2py orbital of the carbon of the CO molecule. This bonding creates a synergic effect that strengthens the bond between the CO molecule and the metal. The total bonding is, thus, M double bond C double bond O. Carbonyls have simple and well-defined structures. For example, tetracarbonyl nickel 0 is a tetrahedral molecule. Pentacarbonyl iron 0 is trigonal bipyramidal. And hexacarbonyl chromium 0 is octahedral. Decacarbonyl dimanganese 0 is made up of two square pyramidal units joined by an Mn-Mn bond. The molecule, octacarbonyl dicobalt 0, consists of two trigonal bipyramids with one edge in common. Let's now study the stability of coordination complexes. The stability of a complex in a solution refers to the degree of association between the metal ion and the ligands involved in the state of equilibrium. Transition metal complex ions differ considerably in their stability. Their relative stability can be expressed in terms of an equilibrium constant called the stability constant. The reaction between the metal ion and the ligand may be represented as M plus Nl in equilibrium with MLN, where N represents the coordination number of the metal ion, M for the ligand L. Note that the charges are omitted for the sake of generality. Now, applying the law of mass action to this equilibrium, we get K is equal to concentration of mLn divided by concentration of M multiplied by L raised to the power n. Here, K is known as the formation equilibrium constant or the stability constant of the complex. The numerical value of the stability constant is a measure of the stability of the complex in solution. The greater the value of the stability constant, the more stable is the complex. The reciprocal of the formation constant is known as the instability constant or the dissociation constant. It is important to note that as free metal ions rarely exist in a solution, complex formation reactions are usually studied in solutions. Metal ions are usually surrounded by solvent molecules that will compete with the ligand molecules and be successively replaced by them. Consider the reaction MH2ON plus NL in equilibrium with mLn plus NH2O. The stability constant for this equation can be written as K is equal to concentration of mLn divided by concentration of MH2ON multiplied by L raised to the power of n. Note that the molar concentration of water is ignored because its concentration remains almost constant. This reaction is assumed to take place in several steps with suitable formation constants in each step. The first step may be written as MH2ON plus L in equilibrium with MlH2ON minus 1 plus H2O. Stability constant K1 for this step is equal to concentration of MlH2ON minus 1 divided by concentration of MH2ON multiplied by concentration of L. The second step may be written as MlH2ON minus 1 plus L in equilibrium with Ml2H2ON minus 2 plus H2O. Stability constant K2 for this step is equal to concentration of Ml2H2ON minus 2 divided by concentration of MlH2ON minus 1 multiplied by concentration of L. Similarly, for the nth step, the reaction can be written as mLn minus 1 H2O plus L in equilibrium with mLn plus H2O. The stability constant for this step can be written as Kn is equal to concentration of mLn divided by concentration of mLn minus 1 H2O multiplied by concentration of L. Here, the stability constants K1, K2 and Kn are referred to as stepwise stability constants. Alternatively, the formation of a complex may be due to the simultaneous addition of ligands to the metal ion. How do you, then, express the equilibrium relations? When only one ligand is added to the metal ion, the equation may be written as M plus L in equilibrium with Ml. The expression for the stability constant for this equation may be written as K1 is equal to concentration of Ml divided by the product of the concentrations of M and L. if two ligands are added to the metal ion, then the expression may be written as M plus 2L in equilibrium with Ml2. The stability constant for this reaction, K2, is equal to concentration of Ml2 divided by concentration of M multiplied by concentration of L raised to the power of 2. Similarly, if N ligands are added to the metal ion, then the equation may be written as M plus Nl in equilibrium with Mln. And the stability constant for this reaction, Kn, is equal to concentration of Mln divided by concentration of M multiplied by concentration of L raised to the power of N. The stability constants K1, K2, and Kn are known as overall stability constants or overall formation constants. The stepwise and overall stability constants are, therefore, related as beta n is equal to the product of K1, K2, K3, and so on up to Kn. Stability constants tend to be very large numbers. To simplify the numbers, a log scale is often used. Thus, the relation between the stepwise stability constants and the overall stability constant can be written in log scale as log beta n is equal to log K1 plus log K2 plus and so on up to log Kn. Consider the formation of the complex tetraamine copper 2 to understand this better. The addition of ammonia ligand to cupric ion may be considered the first step. The stability constant for this step may be written as K1 is equal to concentration of CuNH3 2 plus divided by the product of the concentrations of Cu2 plus and NH3. The experimentally determined value of the stability constant for this step is 1.78 multiplied by 10 raised to the power of 4. When quoted in log scale, its value is 4.25. The second step can be written as CuNH3 2 plus NH3 in equilibrium with CuNH3 2 plus. The stability constant for this step may be written as concentration of CuNH3 2 plus divided by the product of the concentrations of CuNH3 2 plus and NH3. Its value is log 3.61. The other two steps of the addition of ammonia ligands and their stepwise stability constants are as shown. The overall stability constant is simply the equilibrium constant for the complete reaction. Cu2 plus 4NH3 in equilibrium with CuNH3 2 plus. It is given by the expression beta 4 is equal to concentration of CuNH3 2 plus divided by concentration of Cu2 plus multiplied by concentration of NH3 raised to the power of 4. Its value is 1.20 multiplied by 10 raised to the power of 13. In terms of log scale, it is equal to 13.28. Thus, it can be seen that the sum of the logs of the stepwise stability constants is equal to the log of the overall stability constant. The applications of coordination compounds in chemistry, biology, and technology are many and varied. They play a vital role in analytical chemistry, metallurgy, biological systems, industry, and medicine. Let us see how. Let us start with the applications of coordination compounds in analytical chemistry. Coordination compounds find application in qualitative as well as quantitative chemical analysis. If you look at the qualitative methods of analysis, complex formation is of immense importance in the identification and separation of most inorganic ions. For example, when copper sulfate solution is mixed with aqueous ammonia, a deep blue complex soluble in water is formed. This reaction is used to detect cupric ions in the salt. Similarly, the separation of silver ions from mercurous ions in the first group of analysis is based on the fact that while silver chloride forms a water-soluble silver-ammonia complex with ammonium hydroxide, mercurous chloride forms a black insoluble complex. There are numerous reactions in quantitative analysis where complexes are formed. For example, the formation of a scarlet red complex with dimethyl glycoxime is the basis for the detection and estimation of nickel 2+ ions. Similarly, the hardness of water is estimated by titration with the sodium salt of EDTA. During titration, the calcium and magnesium ions in hard water form the stable complexes calcium EDTA and magnesium EDTA. These ions can be selectively estimated due to the difference in the stability constants of calcium and magnesium EDTA complexes. Now let's see the application of complexes in metallurgy. Noble metals like silver and gold are extracted from their ore by the formation of cyanide complexes. Dicyano-argentate 1 and dicyano-orate 1. The metals are displaced from the complex in the solution by zinc. Cyanide complexes also find application in electroplating. For example, in the electroplating of silver, large amounts of silver are held as a complex, potassium dicyanoargentate 1. This provides very little, but all the silver necessary for electroplating. Thus, the articles electroplated with silver or gold are much smoother than those electroplated from a solution of simple metal ions. Metals can be purified by the formation and subsequent decomposition of their coordination compounds. For example, nickel can be purified by its reaction with carbon monoxide to form the volatile complex tetracarbonyl nickel 0, which is decomposed thermally to yield pure nickel. Naturally occurring coordination compounds are vital to living organisms. Metal complexes play a variety of important roles in biological systems. For example, chlorophyll, the pigment responsible for photosynthesis, is a coordination compound of magnesium. Hemoglobin, the red pigment of blood that acts as the oxygen carrier, is a coordination compound of iron. Vitamin B12, cyanocobalamin, the anti-pernicious anemia factor, is a coordination compound of cobalt. Many enzymes that regulate biological processes are metal complexes. For example, carboxypeptidase, a hydrolytic enzyme important in digestion, contains a zinc ion coordinated to several amino acid residues of the protein. Another enzyme, catalase, which is an efficient catalyst for the decomposition of hydrogen peroxide, contains the iron porphyrin complex. One of the applications of coordination compounds is their use as catalysts for many industrial processes. For example, in the hydrogenation of alkenes, a complex metal catalyst, tris-triphenylphosphine rhodium-1 chloride, which is also known as Wilkinson's catalyst, is used. Similarly, another complex metal catalyst, known as Ziegler-Natta catalyst, which is a combination of titanium tetrachloride and triethyl aluminium, is used in the polymerization of ethene. In black and white photography, the unreacted silver bromide on the film dissolves in a dilute hyposolution due to the formation of the complex sodium dithiosulfato-argentate 1. Coordination compounds are also used in medicine. British anti-Lewisite, or BAL, is used as an antidote for arsenic poisoning. Similarly, EDTA is used to treat lead poisoning. Toxic proportions of copper and iron in plants and animals are removed by using the chelating ligands D-pencilamine and desferrioxime B via the formation of coordination compounds. Some coordination compounds of platinum are effective in inhibiting the growth of tumors. For example, cisplatin is used in the treatment of cancer.